Hey guys, welcome to video 27. Today's topic is second order RC low pass and high pass filters. We'd use a second order filter if a first order filter didn't give us fast enough rejection in the stop band. The roll-off rate for a second order low pass is minus 40 dB per decade. The roll-off rate for a second order high pass is plus 40 dB per decade. Now, when we want to create a higher order filter, all we do is cascade first order sections as necessary. The critical frequency for each section is still given by 1 over 2 pi RC. And generally, for a given filter, we're going to set all of the critical frequencies equal. That is, all the sections have the same critical frequency. Now, the 3 dB corner frequency for this filter is not the same as the critical frequency for its individual sections. In order to find the actual 3 dB frequency for the filter, we have to multiply by a correction factor. For a nth order low pass filter, the correction factor is the square root of 2 to the 1 over n minus 1, where n is the order of the filter. For a second order filter, the correction factor works out to be about 0.644. Now, if we were to put a load on the filter, we'd find that this affects the 3 dB corner frequency and the passband response, H sub 0. I'll explain where that notation comes from in a few minutes. For the high pass filter, the correction factor is the reciprocal of the low pass version, and for a second order filter, it works out to be about 1.55. Now, if we were to put a load on the high pass filter, we'd find that that does affect the 3 dB corner frequency, but it doesn't affect the passband response. All right, now, where am I getting this notation, H sub 0, H sub infinity? Well, to see that, let's take a look at the asymptotic Bode plot responses for these filters. All right, starting with the low pass filter, we see that H sub 0 is the asymptotic response in the pass band, and that's the response that we approach as frequency goes towards 0. For the high pass filter, H sub infinity is also the asymptotic passband response, and that's the response we approach when frequency approaches infinity. So there's nothing mysterious about these values. That's where that notation comes from. Okay, now let's talk about cascaded filter sections with no loading effects. Here we've got two first order sections, each with a critical frequency of 1 kilohertz. So when we cascade them, the actual 3 dB frequency is 644 hertz. Now over here on the right hand side, I've got the PSpice simulation for these filters, and the green response curve is what we'd get for either one of these first order sections. We see that the response is 0 dB in the passband, and at 1 kilohertz we're down 3 dB, right? And the roll-off rate is 20 dB per decade. Now overall, when we cascade them, we see that at 1 kilohertz the response is now down by 6 dB. The 3 dB point is occurring at 644 hertz. So if we wanted to correct this red curve and shift it over so that it was down 3 dB at 1 kilohertz, we would either multiply all resistors in the filter by 0.644 or multiply all the capacitors by 0.644. But we wouldn't do both. We pick one or the other. Okay? So doing either one of these operations will take this red curve and shift it over so that its 3 dB frequency is 1 kilohertz. All right, now let's discuss loading of a first order filter section. All right, so what we've got here is a first order filter with RL connected to it. With no load, of course, the critical frequency is 1 over 2 pi RC, and the passband response is 0 dB. When we add the load resistor, we have to use Thevenin's theorem to figure out what's going on. Okay, so for this circuit, RTH is equal to R1 in parallel with RL. All right, and the effective response of the circuit in the passband is now given by the divider equation with R1 and RL. So that is H prime 0 is equal to RL divided by R1 plus RL. Now that's the numerical ratio. If we want it in decibels, we simply multiply 20 times the log of that fraction. All right, and the new critical frequency, F prime C, is 1 over 2 pi RTH times C1, where RTH is simply R1 in parallel with RL. Okay, so that's what we'd have to use to figure out what's going on in this circuit with a load. Now let's do a concrete example. All right, here we've got a first order low pass filter with a load connected, and in this case RL is 1k ohm, so it's really heavily loading this filter down. If this resistor is along the same order of magnitude as this one, we're going to load the filter pretty heavily. Now under no load conditions, F sub C would equal 1 over 2 pi R1 C1, and that would be 1 kilohertz for this filter. All right, and of course H sub 0 would be 0 dB. All right, RTH for this circuit is 1.592K in parallel with 1K, as RTH equals R1 in parallel with RL. And let's pull up our calculator. So R1 is 1592 in parallel with 1000, and that gives us a Thevenin resistance of about 614 ohms. All right, we'll write that here, 614 ohms. That gives us a new F sub C of 1 over 2 pi RTH times C1. Let's pull up our calculator. Whoops, where are you? There you are. Okay, so we've got 2 times pi times 614 times 0.1 times 10 to the negative 6th. We take the reciprocal. So that gives us a new critical frequency of about 2.6 k ohms. All right, so let's write that over here. 2.6, I'm sorry, k hertz, not k ohms. And our response is given by the voltage divider ratio. So that's going to be H sub 0 equals 20 log RL over R1 plus RL. And let's pull up our calculator. RL is 1000, and 1592 plus 1000 is 2592. So it's 0.385. We take the log times 20, and we should be down about negative 8.3 dB, negative 8.3 decibels. All right. And looking at our PSpice simulation over here, we see that with no load, of course, H sub 0 is 0 dB. Our corner frequency or critical frequency occurs at 1 kilohertz. And when we connect the load, our passband response is minus 8.3 dB, which is what we calculated. And when we're down 3 dB from there, it'll negative 11.3. That occurs at 2.6 kilohertz, which is again what we expected to see. So here's a PSpice simulation that helps to show that what we're doing here actually is valid and makes sense. You could build the circuit and find the same results, but you know, that's not something practical for me to do in a presentation like this. All right, now let's go through an actual design example for a second order low pass filter. All right, I don't have many constraints. All I'm asking for is the 3 dB frequency equal to 1 kilohertz. Normally the first thing I'll do in a design like this is pick the capacitor values, okay? And I'm going to start with C1. And I like to keep my capacitors between 1 microfarad and maybe 100 picofarads when I'm dealing with audio frequencies. All right, so I'm just kind of arbitrarily going to pick C1 equals 0.047 microfarads. And then we'll find R1 by solving the F sub C equation, which gives us R1 equals 1 over 2 pi F sub C times C1. All right, let's pull up our calculator and see what resistor we need here. Okay, so 2 times pi times 1,000 times 0.047 times 10 to the negative 6th gives me about 3.4 k ohms. All right, so 3.4 k ohms. Now, I could just use the same values in this second section, but that would really load the first section down. Okay, to minimize loading, what I like to do is make this resistor at least 10 times bigger than this one. And in order to keep the critical frequency the same, I have to divide this capacitor by the same amount. So if I make R2 equal to 10 R1, that gives me 34 k ohms, right? And C2 is equal to C1 divided by 10. That gives me 0.0047 microfarads, okay? So the product R times C is the same for both sections, all right? But remember, because this is a second order filter, we have to apply a correction factor, right? So what's the correction factor? It's 0.644 for a second order filter. So let's come back over here and let's multiply our resistors by 0.644. So the actual R1 value is equal to 0.644 times 3.4 k ohms. And what does that give us? Let's see. 0.644 times 3400 is about 2.2 k ohms. All right, so that's about 2.2 k ohms. And fortunately for us, that's a standard resistor value. Sometimes when you go through these procedures, you get crazy capacitor or resistor values, and you just have to kind of start over again, picking a different starting value and going from there. But this is perfect, okay? 2.2 k is a standard value. And that means my actual components for this circuit are going to be R1 is equal to 2.2 k ohms. R2 is 10 times that, or 22 k ohms. C1 is still 0.047 microfarads. And C2 is 1/10 of that, 0.0047 microfarads. And there we have our second order low pass filter with a 3 dB frequency of pretty close to 1 kilohertz. All right. If you have access to PSpice, I recommend that you maybe draw this circuit up and see what it gives you. Okay, that would be good practice. All right. Now, let's go on and talk about the high pass circuits for a minute. All right, the second order RC high pass filter, and as usual, the critical frequency for each section is 1 over 2 pi RC. It rolls off at plus 40 dB per decade. And cascading a second section doesn't affect the passband response, but if we follow the rules I just developed in the last section, if we set R2 equal to 10 times R1, then we can find the 3 dB frequency using this correction factor. All right, so remember, scaling the impedance of the second section reduces loading on the first section, and it makes this equation more accurate. Okay? Now, let's finish out by giving you guys a shot at this. Okay, so what we've got on the left-hand side is that first order low pass, but now we've got a load of 10 k ohms, and what I'd like you to do is find the Thevenin equivalent, the effective critical frequency, and the passband response. And then design this second order filter for a 3 dB frequency of 500 Hertz using C1 of 0.068 microfarads. Okay, and that's all I've got for you for today. I know that was a lot to absorb, but hang in there, it'll come, and I'll talk to you later.